Should I start? Okay. Let me just double check that I put the right Lagrangian here. Plus the gluons. So I got many excellent questions during the break, and I want to point out one thing. So up until this point, the introduction of these Wilson lines came through a different door compared with HQET, where we used it as a trick to eliminate the coupling to gluons. They really came to get rid of this inverse covariant derivative. The inverse derivative is an integral, so the non-locality is true. This is unavoidable in this theory. It's a truly non-local theory on the light cone. And the Wilson lines were needed to make that step from the inverse derivative to this integral form. However, the Wilson lines are also needed at this point for a different reason, because remember that in field theory, you cannot simply write down non-local operators. If I write an operator in a scalar theory, for instance, phi dagger x, phi of y, that's non-local, that immediately violates gauge invariance, right? If I perform a gauge transformation, this will be transformed with some function u dagger of x, and phi of y will transform with some function u of y. So a local gauge transformation, and this in general at different points is not equal to 1. So this violates gauge invariance. And the Wilson lines save the day, because we have two Wilson lines here. A Wilson line at point x and a Wilson line dagger at point x plus t n bar. And, you know, if x is here and I go on the n bar light cone, so this is the direction n bar, I can be at a different point, y equal x plus t n bar. And the first Wilson line basically takes you from here to infinity. And then from infinity, you come back with the second Wilson line to this point. So in a way, you turn around here and you come back to this point. And these two paths of the Wilson line, they cancel out. Okay, because you run them in different orders. And what you end up with is a finite length Wilson line from here to there. So that's what remains. And that's called the Wilson link. And if you write non-local field products with Wilson links in between from y to x, then actually this is gauge invariant. So whenever you see in the literature a non-local operator and they enter, for instance, in the definition of Parton distribution functions, you see these Wilson links. And that's the way the theory is gauge invariant. So the Wilson lines are also needed here. And in the end, they are always needed to make non-local expressions gauge invariant. Okay, so they have several purposes. The way we introduced them before, we didn't pay attention to gauge invariance, but they're really needed for gauge invariance. I didn't say that. At the moment for this Lagrangian, this is irrelevant because we are only in one sector here. So your statement is true, it's also relevant, but not at this point, because here I'm only in the collinear sector. When I have collinear and ultrasoft, indeed, then I have different gauge transformation. We'll come to that. Okay, so this was just a side remark to give you a little bit more insight into what these Wilson lines are good for. Now I want to discuss the coupling to the ultrasoft gluons. So this is now the piece C plus ultrasoft. And I'm going to work, I gave you before order lambda to the 4 and order lambda to the 5th. Order lambda to the 5th is power corrections, okay? I'm not going to discuss power corrections. I'm going to stick with the leading order Lagrangian for the rest of these lectures. And then there was a single term in this interaction. And the single term was in the first piece here, where in addition to n dot d collinear, which is order lambda square, we add the ultrasoft piece here, which is also order lambda square. And then this ultrasoft piece defines the interaction of the collinear quark with the ultrasoft gluon. And it's of that type. Okay, so it's simply the piece that came from the covariant derivative, because this is order lambda squared and this is also order lambda squared, so they both contribute at leading power. And there's also some pure glue terms which couple collinear gluons to ultrasoft gluons. There are no ultrasoft quarks at leading order. So there are no ultrasoft quarks at leading order. In fact, nowadays people study power corrections a lot in SCT, and they mainly deal with the role of ultrasoft quarks there. Now let's look at the structure of this interaction, because nothing comes for free in SCT. Get used to it. Whenever you think something is really simple like this, there's always a tweak to it. This is extremely simple, but we'll need to modify it. If you look at the structure of these interactions, what is this? It's very simple. This is the quark-gluon vertex. So we have a collinear quark coming in, we have a collinear quark going out, and we have an ultrasoft gluon. So let me write momenta here, PC, PC prime, and K ultrasoft. And let us remind of the scalings here. So the scalings are lambda square 1 lambda for the collinear momenta, and all components lambda square for the ultrasoft momenta. Okay, so you see something that's a bit awkward, namely the first component here has the same order, both for ultrasoft and collinear, but the other two components are power suppressed relative to the scaling of the collinear momenta. So if I start with some known momentum PC, with that counting, what I'm doing here now is I add, for instance, to this order 1 component, I add a small order lambda square component, which is something I shouldn't really do, because I should always perform my Feynman integrants in powers of lambda. This is a vertex rule. It will enter my Feynman integrals. Right, so I have a problem here. We can spell this out in equations as well. PC prime is PC plus K ultrasoft. And if I write this out in components, I get n dot PC plus n dot K ultrasoft, n bar over 2 plus n bar dot PC, n bar dot K ultrasoft, n mu over 2 plus PC perp plus K ultrasoft perp. And of course, this is order lambda square, this is order lambda square, so here all things are good, but this is order 1, this is order lambda square, this is order lambda, this is order lambda square. So really, those guys, I should expand them. So, you know, if I should not use this as a Feynman rule at this vertex, because it will introduce some power suppressed pieces inside the integrand, and I should always expand these integrants in powers of lambda. So really, what I should keep here is only the terms which have the correct power counting. So the first term, it's okay. This is fine. But for the remaining two terms, I should only keep the collinear piece. And you know, it doesn't matter that this is smaller than this, because they come with different vectors here. For collinear momenta, we know that the scaling is not homogeneous. I just need to, what I should not do is add something that is a correction to the corresponding collinear momentum. That I should not do. So here I should only use the collinear ones plus power corrections. And if I work to subleading power, then I should keep these terms, but they would contribute to the subleading power amplitude and not to the leading power amplitude. So you see, what is this? This is PC, the full collinear momentum. And now the only part of the ultrasoft that enters is this guy here. Okay, it's only this one component that enters. And that is what we called K ultrasoft plus mu. So remember, a 4-vector with a plus index was just defined to be n bar dot this vector times n, or n times this vector n bar mu over 2. So it's just the plus piece of the ultrasoft momentum which we should keep here, and the power corrections we should neglect. Now, how do you implement this at the level of Feynman rules? So basically, the Feynman rule should really be, the correct Feynman rule should really be for this vertex. You have a collinear momentum coming in, you have this vertex with a K ultrasoft, and what goes out has momentum PC plus K ultrasoft plus, which is the same as PC mu plus n dot K ultrasoft n bar mu over 2. So this is the Feynman rule, which in particular means momentum is not conserved in this vertex. I have a momentum coming in here, I have a momentum coming in here, but what goes out is only a piece of that momentum. So momentum is not conserved. Now, don't call the New York Times and say, we just discovered momentum non-conservation. Of course not. Of course, in QCD, momentum is conserved at every vertex. And if you want, you can write delta functions of the 4 momenta, ensuring that. All I'm telling you here is we should also perform in the arguments of these delta functions a lambda expansion. And then there might be a small piece that we need to expand out, and then if we work to higher orders, it will come back in the higher order terms. So when you add everything together, you will find that momentum conservation is reinstated. But at the level of this Feynman rule, in order to do the proper power counting, this is the momentum we need to assign. Now the question is, how can you implement this in the Feynman rules? And the trick to do that is called the multipole expansion, which maybe you remember from your E&M courses when you discuss potentials of charge distributions at long distance in Maxwell theory. I want the plus component of the ultrasoft momentum. I can do the following trick. If I have an ultrasoft field at position x in interactions with collinear fields, only in interactions with collinear fields, I can do an expansion of the argument x. Because what does momentum conservation mean? Well, we have a point x where several fields come together, and then we get a phase factor, e to the I, and then we get a momentum for each field that comes together at this vertex. And then when we integrate over d4x, we get a delta function setting the momenta at the vertex. So this is some vertex with n lines going in, okay? And then the sum of the momenta is set to 0. If I want, only this momentum x plus, K plus, I could, for instance, write here PC plus K ultrasoft plus times X, but that in the phase factor. But this is the same as writing plus K ultrasoft times X minus, where X minus is n bar dot X times n over 2. Because K ultrasoft times X minus is the same as n bar dot X n dot K ultrasoft over 2, which is the same as X times n bar over 2 n dot K ultrasoft, which is the same as X dot K ultrasoft plus. So you always have to remember that in dot products, plus and minus components come together. So in other words, if I expand this field around X minus, then for the ultrasoft, I will automatically in the phase factor get this combination, which has the same effect as only putting the K plus component there, which is exactly what I want to get. And again, you can formalize this. You can expand this field about X minus, and then you'll get higher order terms. And the higher order terms can be written down. So this is at, X equal to X minus after you do the expansion, and the next term would be X plus times D minus plus X perp mu over 2 times D mu perp phi of X at X equal X minus, and so on and so forth. And these terms, if you assign scaling to them, this counts like lambda to the minus 1, this counts like lambda squared, so this is an order lambda correction. And here, this counts like, so X basically, this is ultrasoft fields in interaction with collinear fields, so the X counts like a collinear X. So remember X collinear, the scaling was 1 over lambda squared, 1 over lambda. So this is plus minus perp. So X plus counts like order 1, X perp counts like 1 over lambda. And the derivatives are derivatives on ultrasoft fields, so the derivatives always count like each, like order lambda squared. So you see this term here is order lambda square suppressed. So you get the leading term, a 1 over lambda correction, an order lambda square correction, and so on. So this is called the multipool expansion, and at leading order for ultrasoft fields interacting with collinear fields, you simply replace X by X minus. And that gives the correct answer. And therefore, really the correct answer for this Lagrangian, so after the multipool expansion, the correct answer is the following. L collinear plus ultrasoft at leading order is C bar of n at point X, n bar slash over 2, I sort of G, should look at what I'm writing here. GS n dot A ultrasoft at point X minus Cn at point X plus pure glue terms. And in the pure glue terms, it's the same thing. The collinear fields are at point X. The ultrasoft fields are at point X minus. Okay, I don't know. Was it clear? Expanding this field around X minus makes sure that in momentum space, only the plus component of the ultrasoft momentum enters the vertex, and only the plus component of the ultrasoft momentum is of the same order as the plus component of the collinear momentum. All the other components of the ultrasoft momentum would give rise to spurious power corrections, which we don't want. Okay, so at this point, there's a slide now with the leading order SCET Lagrangian. We'll only discuss leading order, but I think it should be clear that at least to write down subleading corrections to the SCET Lagrangian is not difficult. You had all the expressions on the board. Just take the lambda to the fifth term, plug in what we do here. You do the multipole expansion, this would be another term that adds at order lambda to the fifth. So you just have to do the bookkeeping, but it's not difficult, it's just Taylor expansion. But we'll look at the leading order term. So what is the leading order term? Well, we had it all. And it's almost a waste to write it down again. N over 2, I n dot d collinear Cn minus Cn bar I d slash collinear perp W collinear at x minus I times integral dt W dagger I d perp collinear Cn at x plus Tn bar. So that's the collinear Lagrangian plus now the anticollinear Lagrangian. Same with C to C bar and N bar interchanged, including the Wilson lines. The Wilson lines here have N bar in it, and the Wilson lines in the collinear sector would have N in it. So this is LC, this is LC bar. Now the ultrasoft Lagrangian, Q ultrasoft, ID slash ultrasoft, Q ultrasoft, like in QCD. Nothing changed there. And now the interaction terms, C n of x, n bar slash over 2 gs n dot a ultrasoft of x minus Cn of x. That's L collinear plus ultrasoft. And then we also have the anticollinear sector with everywhere n and n bar interchanged. What does that mean for the argument of the ultrasoft field? What does that mean for the argument of the ultrasoft field? When it interacts with anticollinear, x plus, what else should it be? And of course, that just has the effect that instead of n dot k, then n bar dot k enters, because for the anticollinear, that's the small component. And that's the only thing that matters. Plus pure glue terms. And again, note the important fact that ultrasoft quarks do not enter at leading order, except here when they interact with themselves, but no interactions with the collinear sector, only via gluons. exactly. The coordinates are collinear because this is only in interactions with collinear fields, where there are collinear momenta here and one ultrasoft momentum, and then the x is a collinear x, so to speak. Yeah, it's always you always have to take the larger of the momenta that come together in a given vertex. That defines the scaling of the measure. Good point. Okay, so now we could go to higher orders. We won't. We could derive Feynman rules from this Lagrangian, and I almost want to say we won't. The Feynman rules are weird. So for instance, the quark propagator, okay, for two Xi fields, it's the inverse, you have to take the inverse of this differential operator. What you get for the quark propagator is n//2 I n bar dot p divided by n dot p n bar dot p plus p perp squared plus I epsilon. That's what you find. And you can write this, believe me, you can write this as Pn IP slash over P square plus I0 I epsilon times P n bar. So you see that this is really just the ordinary quark propagator in QCD, and then you apply the projection operators which are contained in the Xi fields. So the Xi fields are Pn times the Xi fields are Pn times the original field. So just take the original propagator and multiply from left and right with the projectors, and that's what gives you this Feynman rule. Let me just write, I don't want to write all of them because they're really useless in some sense. You never use them. Let me just show you that they're ugly. So this is collinear, so collinear quark, collinear gluon. This was also collinear quark. For instance, the Feynman rule for this is IGS TA, and now n mu plus gamma mu perp p slash perp over n bar dot p plus p prime perp slash gamma mu perp over n bar dot p prime minus n bar mu p perp prime p perp over n bar dot p prime n bar dot p, and the whole thing times n bar slash over 2. So hugely more complicated than in QCD, and moreover, different orders in power counting. Order 1, order lambda, order lambda, order lambda squared. And moreover, it doesn't stop there. You have Feynman rules with collinear guys, collinear quarks, and an arbitrary number of collinear gluons. And the reason is that the Wilson line is an exponential of the gluon field. You can pull as many gluons from that Wilson line, and the exponent is unsuppressed. It was the order 1 component of the Wilson line. So infinitely many complicated, just write complicated, and infinitely many. In the founding papers of SCT, people have performed calculations using these rules. In practice, you never do it. You never do it. What you remember is that this part of the Lagrangian, which gives rise to all these ugly rules, this is an exact rewriting of QCD. So just say Xi is Pn times psi, and psi has the Feynman rules of QCD. So you work in QCD, you apply your projectors, and it's a much easier way to do the calculation. nevertheless, you know, this is the Lagrangian, and it's the first term that gives rise to all these messy rules, but just we do rewriting of the theory. Lecture 6, if you go online, has 3 parts. This was the first part. The second part I put as a reading assignment. It's not essential to follow this course. It's very useful to have as a knowledge. So this reading assignment, the first discussion is about gauge invariance. That's your point, that when we have this theory, we have to be careful when we consider gauge transformation, because a local gauge transformation takes a field and multiplies it with a matrix U of X, which is an element of the group, SU3, okay? But U of X in momentum space has arbitrary momenta. It's just the Fourier transform of an arbitrary function U of X. So if you're not careful, you take a collinear field and apply an arbitrary gauge transformation, it kicks you out of the collinear sector. And that's not what you want, okay? So we say that SCET has a residual gauge invariance where in the sector of collinear fields, you only allow gauge transformations whose Fourier transform has collinear momenta. That's called a collinear gauge transfer. It's very natural, okay? You are in the collinear sector, you only allow gauge transformations which keep you in the collinear sector. And ultrasoft gauge transformations would only have ultrasoft momenta and keep you in the ultrasoft sector. That's called residual gauge invariance, and that's discussed in the first 3.5 pages of this reading assignment. Then there is a non-renormalization theorem due to Beneke et al. I already mentioned it, that this Lagrangian is not renormalized, but actually it's more powerful. This entire leading order Lagrangian is not renormalized, including the couplings to ultrasoft quarks. And again, the reason is we have not integrated out anything. We have just performed expansions in lambda, but we have not really integrated out anything. Everything is still there in the higher order terms in lambda if we keep them. And then the third point is reparametrization invariance, thanks to Anish, which is the statement, well, the most important, reparametrization invariance has to do with redefinitions of n and n bar. You can do small redefinitions. You can, for instance, when I tell you the jet goes in this direction, what exactly do I mean? Well, I mean, you define a jet algorithm, and with that jet algorithm, you construct a jet axis. And maybe somebody else takes a slightly different jet algorithm and finds a slightly different jet axis. So clearly, the definition of n and n bar is not unique. So reparametrization invariance has 3 different transformations. Basically, it says you can change n by a small amount, an amount of order lambda. N defines the direction of large energy flow, but if you twist it a little bit, just a little bit of order 1 over lambda, of order lambda, the physics doesn't change. If you turned it by 90 degrees, you would do nonsense. The jet goes there, you cannot point it in this direction. But if you change a little bit, that's okay. So you can change n and n bar, that is type 1 and type 2 reparametrization. The most important one is type 3 reparametrization. So reparametrization invariance. And that's a very useful one, because remember, we had introduced these n and n bar vectors such that n square is 0, n bar squared is 0, and n dot n bar is 2. And that allows for an obvious symmetry. If I take n and rescale it to some, whatever, alpha times n, and n bar, you rescale to 1 over alpha times n bar, then these 3 relations are still valid. If something squares to 0, it doesn't matter if you change the length, it's still 0 when you square it. And if you rescale them in an inverse way, the dot product is invariant. Okay? So type 3 reparametrization is this transformation. Everything should be invariant under this transformation. And actually, physically, what this is a longitudinal Lorentz boost. if I have a two-jet configuration and I boost myself along the jet axis and I don't boost so far that I overtake. So this alpha should be order 1 in order not to upset the power counting. So alpha should be order 1. So if I have this two-jet event and I do a moderate Lorentz boost along the jet axis, I still see two jets going back to back. One will have a slightly lower energy, the other will have a slightly larger energy, but the directions are still intact. Okay, so everything must be invariant, in particular under this set of reparametrizations. And for SCET, that means n and n bar should always come in pairs. And you can check that for each term. You have an n here, you have an n bar. You have an n bar here, which means that t should scale like n. And that immediately shows you that I have forgotten something, namely n bar slash over 2, which I've forgotten to copy, right? Because t must scale like n, and so when there is a t, there must also be an n bar. And here, there's an n bar, there's an n, there's an n, there's an n bar. So when when you get the task, whatever, construct SCET operators of a certain order in power counting, that thing that you always need to make sure that whenever there is an n, there needs to be an n bar. That is called type 3 reparametrization invariance. And that is also briefly discussed, and all the other reparametrization invariants that also discussed on the reading assignment. So, no, momenta are measurable things, no? So if you give me a quark with a certain momentum, it's a quark with a certain momentum. But when I decompose that momentum into light cone coordinates, it's not unique, what I call n and n bar. That's the statement. So it's like a choice of, I need to have the z-axis aligned with the jet, but aligned with the jet is not an absolute statement. So you would change the components slightly. The scaling should remain intact, yeah. Exactly, that is also why if you want to turn n away from the jet direction, it has to be by an order lambda, small amount. Good, so, yes. No, also the jet axis changes. I just wanted to say n is not absolutely defined.
Yeah, but when you're equating to RPI invariance, do you mean that color connections are dropped and after that this is equivalent to?
It's really just, we introduce these reference vectors into the theory. And it's clear what we mean by them, but it's not absolutely defined. For instance, I could say, take the most energetic particle and pick n to be that direction. Or you can say, take the average of all the momenta. Or you can say, use the whatever, Cambridge-Aachen, reconstruct the jet and tell me what the jet axis is, or the thrust axis, or whatever. However you define, you have a set of particles moving in that direction, but how exactly you define the jet axis is not unique, but all definitions, if they're sensible, they will just differ by order lambda corrections. Okay, that's what is meant here. I think hopefully it's clear, otherwise we can also bring it back up in the question session. So next section, matching, because this is really important now, matching of the two jet current. Because so far we have just discussed the Lagrangian, now we want to do something with that Lagrangian. And the most important, one of the most important applications is this type of situation, C plus E minus 2 gamma to 2 jets, okay? Higgs is the same, in the Higgs case, I have proton-proton to Higgs is the inverse of this. I have a collinear gluon and an anticollinear gluon. I make a Higgs. In this case, I have a virtual photon, and I make a collinear quark and a collinear antiquark. So the external operator here is psi bar gamma mu psi. And naively, you would say, well, very easy. Nothing easier than that. obviously one quark flies off to the left, one quark flies off to the right. One of them is collinear, the other is anticollinear. So I would write a collinear spinner, I would write an anticollinear spinner, and now I should put gamma mu in between. But gamma mu I can decompose in the light cone basis. There is a term with n slash that is killed by this spinner. There's a term with n bar slash that is killed by this spinner. So the only part of gamma mu that survives is the perp piece. And this is the collinear quark, and this is the anticollinear antiquark. Okay, so that's what you would expect. And of course, that's also in some sense true, but it cannot be the correct answer. Why can it not be the correct answer? Well, that's part of the reading assignment, because as I discussed earlier, when we consider gauge transformations, we can only transform collinear fields with collinear gauge transformations and anticollinear fields with anticollinear gauge transformations. And those two things are not the same. So if I perform a collinear gauge transformation, so under a collinear gauge transformation, basically Cn of x goes over to u collinear of x, Cn of x, but the anticollinear field simply does not transform. If it were to transform, it would be kicked out of its momentum shell, because the collinear gauge transformation corresponds to collinear momenta, and I cannot add a collinear momentum to an anticollinear field. And clearly this operator would not be invariant, and likewise there are anticollinear gauge transformations under which the collinear fields would be invariant and the anticollinear fields would transform in a non-trivial way. And this operator would not be invariant under any one of them. Okay? How do we fix this? With Wilson lines. Okay? In a similar way I told you when I discussed this thing, I basically said that the product of, where did maybe I erased it. I basically said that a field times a Wilson line is gauge invariant. If we look how this is all discussed in this reading assignment. If you look how the Wilson lines transform, so the collinear Wilson line also transforms with the same gauge transformation. Strictly speaking, there is another gauge transformation at infinity here. But if we agree that at infinity, at the end of the universe, all quantum fields vanish, then this Wilson line, we can put this gauge transformation, we can put to 1, and then the collinear field and the collinear Wilson line transform in the same way, and the anticollinear Wilson line transforms under anticollinear gauge transformations. And this is such that the product W dagger psi of x is gauge invariant. This was exactly the reason why I said earlier that we can have this field W dagger psi at a different point from this field, because in that combination they are actually gauge invariant under collinear and anticollinear gauge transformations. Okay, so you see how we need to fix up this operator. What we need to do is we need to multiply these fields with the Wilson lines. So we add here W dagger, and we add here W anticollinear. And then we put the gamma mu perp in between. And now we have a gauge invariant operator. It's invariant under both collinear and anti-collinear gauge transformations. There's also ultra-soft gauge transformations. And they're also discussed in the reading assignment. Let me just tell you that if I evaluate these fields at 0, so if I study this operator at 0, and for one external current, I can always do that. I can always call the space-time point. When my weak interaction happens, for example, I can also always decide that this happens at the origin. Then this is also invariant under ultra-soft gauge transformations. However, if I want to change this to a different point, there's a subtlety with the ultra-soft gauge transformation. And this subtlety you will explore in the second problem on the second homework set. It has something to do with multipole expansions again, but I leave it up to you to consider this. I'm just saying that, yeah, I'm saying that this, you know, if I want to represent this operator in SCET, a collinear quark and an anti-collinear quark, this is a gauge invariant way to do it. Whereas without the Wilson lines, it would not be gauge invariant. Now again, one thing is math, the other is physics. You can say, well, you know, great, but I know what this means. Whenever you sell me a Wilson line, I know that it corresponds to such things, you know, arbitrarily many gluons connected to this object. So, you know, how do you know this makes sense? What are where do these gluons come from? Why? This is just a quark-antiquark current. Why in the effective theory it contains in its definition infinitely many gluons? What's the physics? Okay, and there is very good physics. So, you know, you can get this from gauge invariance. You could also, I claim now, get this from matching. Because to go from here to there, we need to do matching. Now, normally matching is trivial at tree level, and then at loop corrections, you get alpha S corrections, which go inside the Wilson coefficients. In this case, tree level matching is highly non-trivial. And what one can show is that these Wilson lines also follow from tree level matching. What is matching? Matching means I integrate out hard quantum fluctuations. Let's see how this works. This is a virtual photon coupling to a quark-antiquark. Okay, so the incoming quark is collinear, the outgoing quark is anti-collinear in my case. That's what we call the two-jet current. This is my gamma star, okay, my vector current. Really, I will not write down electric charge and polarization vector. This is just a vector current. So this is my current. I can now do the following thing. Imagine I want to add a collinear gluon to this vertex. Imagine I want to attach a collinear gluon to this vertex. Okay, so this is the vertex in QCT. In SCET, what do I have in SCET? In SCET, people sometimes use dotted lines. It's just terrible on the blackboard. They use dotted lines to draw collinear fermions. I don't know, can you see this? This dotted line is a collinear fermion, an anti-collinear fermion. And now I want to attach a gluon here, a collinear gluon. So, I mean, I'm really studying, what I mean is I really study a 3-point function, collinear guy going in, anti-collinear guy going out, and the gluon coming out, and I want this to be a collinear gluon. Okay? And now I can ask myself, how do I get this in the effective theory? Well, from this operator, I get it because there are collinear gluons here. So at tree level, I know that in in the effective theory, this is the diagram that I just drew, where the gluon comes from this vertex. But the question is, what diagram in the effective theory, in the full theory, would give me, you know, such a contribution that I get a point-like interaction with this gluon? Well, you know, where can I attach the collinear gluons? There's exactly two possibilities. I can attach it here, and I can attach it here. So this is my two possibilities. Now, you tell me what happens. If I start with a collinear quark and I attach a collinear gluon, what do I get? What do I get? A collinear quark, right? Collinear plus collinear stays collinear. In this diagram, I have an anticollinear quark coming out. If I attach a collinear gluon to an anticollinear quark, what do I find for this propagator? Hard. Excellent. Now, going to the effective theory, what is the corresponding diagram for this guy? It will look just the same. It's simply this. Collinear quark, anticollinear quark. And this is just my Lagrangian, which describes how collinear gluons interact with collinear quarks. Okay? So, you know, from here to here, it's three-level matching of the trivial type. I have this diagram in the full theory. I have the corresponding diagram in the effective theory, and they will be the same when I evaluate them up to maybe higher powers in lambda. But actually here, they will even be the same. But what about this guy? In this guy, I have a hard propagator. And when I have a hard propagator, what happens to a hard propagator when I go to the low energy theory? Think of Fermi theory. What happens to this propagator? And it shrinks to a point. Exactly. So this guy looks like this in the effective theory with a non-trivial Wilson coefficient. Okay? Is it clear? Yeah? And we will actually do this calculation now and compute what this Wilson coefficient is. But before we do that, let me tell you that here we do three-level matching. So, you know, it's not that the loop expansion saves us. Let me just say that this is not the end of the story. I can look at diagrams of that type in the full theory. So here I have my collinear guy, my anticollinear guy, my photon. I can now attach here, you know, in a complicated way, I can attach anticollinear gluons, and I can attach collinear gluons here, as many as I want, right? And all of these propagators here will be hard. I can also do something like a collinear here and an anticollinear here, then this is also hard. All of these propagators need to be integrated out, but this is tree-level. It's all tree-level, for God's sake. Nothing, it never stops. Infinite trees of gluons. As long as you have hard propagators, you need to shrink them to points. And we will see that this is exactly what these two Wilson lines do. They describe these infinitely many matching calculations. They're all absorbed into this single beautiful expression. Okay? We'll prove this. This is an all-order statement. We'll prove it for one gluon. In the papers by Stewart, Bauer, Pierschel, et al., the SCET founding papers, you see the calculation with two gluons, where it's already non-trivial. You can have a 3-gluon vertex entering there. And they prove that at the 2-gluon level, what you get is exactly reproduced by the Wilson lines. So let's do this calculation. And the one I'm going to do is, so for some reason I want to attach, what did I do here? I think I did it. Yes, I want to, the diagram in the lower left there. That's what I want to calculate. So in momentum P coming in, collinear, momentum P prime going out, anti-collinear, and here I have a collinear gluon. And I want to have inflowing momentum K, polarization mu, color A. And here's my photon. So I want to compute this diagram. This diagram is easy to compute. If I start here, I get my anti-collinear spinner with momentum P prime, gamma mu from the gluon, quark propagator P prime slash minus K slash over P prime minus K squared. Then the electromagnetic vertex. There is a factor here of the strong coupling, which I forgot. Sorry, there's also a color matrix, which I forgot. And then there is, for the photon, you want, I can put the polarization vector for the photon. No, sorry, for the, what am I doing? Sorry, let's put this up. I'm sorry. Don't know why I didn't just copy it from the page. So at the photon vertex, at the gluon vertex, IGS, TA, and now for the gluon, the polarization vector epsilon slash of K. Sorry, this is what I wanted to write down. Then the quark propagator P prime slash minus K slash over P prime minus K squared. Gamma mu for the photon and U of P. And okay, so now I need to expand. So let's do this carefully. So basically I take my polarization vector and I will now decompose it in the usual way as n bar dot epsilon times n slash over 2 plus n dot epsilon times n bar slash over 2 plus epsilon perp slash. It's a collinear, that's the collinear gluon. Okay, let me put a collinear here. And this is also collinear. And then here in the propagator, I have, I can write this propagator as P prime squared plus K squared minus 2 P prime K, and that I can write as n dot P prime n bar dot K plus n bar dot P prime n dot K plus P prime perp dot K perp with a factor 2. That's the propagator. And now gamma mu and U of P, the collinear spinner, and this is the anti-collinear spinner. Now I assign my power counting. So n bar dot epsilon for a collinear field, that's the n bar component, that's unsuppressed, lambda to the 0. That's the n component of the collinear gluon field, that's lambda squared suppressed. The perp component is lambda suppressed, so this is the leading one here. Here I get collinear momentum squared is order lambda squared, K squared is also collinear momentum order lambda squared. One is collinear, one is anti-collinear, doesn't matter. For the anti-collinear momentum, the n dot P component is order 1. For the collinear gluon, the n dot K component is order 1. Whereas this is order lambda square times lambda square, and this is lambda times lambda. So you see here, it's this piece which is leading, and all the other pieces are subleading. So if I just keep the leading effect. I get an I, and an I makes a minus G sub S. An N bar dot epsilon of K for the gluon. And excellent. What happened to it? Oh, I forgot it. Sorry. P slash, yeah, it's absolutely right. So I get N dot P prime minus K times N bar slash over 2 plus N bar dot P prime minus K N slash over 2 plus P prime minus K slash perp. Thank you. Yeah, I was looking for something in the numerator. N dot P prime is order lambda square. No, P prime is anticollinear. So this is actually N dot P prime is order 1, N dot K is order lambda square. N bar dot P prime is order lambda square, N bar dot K is order 1. And the perp components are order lambda. So here we have a leading term here and a leading term there. Yeah, sorry if this is a bit messy. And now we just keep the leading stuff and we throw away everything else. So I times I is minus 1. The GS I pull out the N dot epsilon, N bar dot epsilon. Now I have my anticollinear spinner, an N slash over 2 from here. This I can all forget. Now here in principle I have 2 leading terms, but this one also comes with an N slash. If I put this N slash next to this N slash, I get 0. So I only end up with this guy, which is N dot P prime times N bar slash over 2. And downstairs, I only have this guy. So minus N dot P prime N bar dot K, and then gamma mu and U C P. Now you see that this guy cancels this. And at the end of the day, this minus sign cancels this minus sign. And I forgot the TA somewhere, the color matrix. So I can write this as U of P prime N slash N bar slash over 4. GS TA N bar dot epsilon of K divided by N bar dot K times gamma mu times UC of P. Now you see here, there's nothing but Pn, our projector, Pn, which is also the same as Pn bar bar. So you can apply this to the left or to the right, and it will just give you the x's. It will just be the projection on the x's. So that what we get here is basically this, we get the xc n bar, gamma mu perp xcn, and then here gsta n bar dot epsilon k divided by n bar dot k. Okay. At leading power plus power corrections, but at leading power, this is what we get. Very simple expression. And now I claim that this is nothing but a one gluon matrix element of the collinear Wilson line WC dagger, which is part of the definition of this operator here. And this is the last thing we do. before we finish the lecture. And I promise you, if you ever do this for the 2-gluon matrix element, you really see miracles. You won't believe that it works, but it works. But it's non-trivial because the color algebra, then here it's just TA for 1 gluon. We have 2 gluons, it's TA, TB, TB, TA, depending on the order. And then you can have the triple gluon vertex, which is an FABC. When you add up all contribution, when the dust settles, you get exactly what you get from the Wilson lines. So the Wilson lines are needed for gauge invariance, but they're also needed to do a bunch of other miracles, so that, you know, they really account for this 3-level hard matching. So let's compute the matrix element of the Wilson line. We need the collinear Wilson line because we pulled out a collinear gluon. If we pulled out an anticollinear gluon, we would get it from the anticollinear Wilson line. So I have an initial state gluon because I chose to let it flow into the diagram. So it's an initial state particle with momentum k. So I have a gluon here with polarization epsilon on momentum k, and I want to pull this from the Wilson line. Okay? So the Wilson line is a path-ordered exponential. Since it's a daggered Wilson line, we have to also reverse the path ordering, but the path ordering is not going to play a role for us because we only pull a single gluon out there. So n bar dot A collinear Tn epsilon k. So we need the 1 gluon term. This is minus IGS, an integral over t, minus infinity to plus infinity. And, you know, if we contract the gluon field with the external state gluon, the field itself is replaced by the polarization vector. And then we get a phase factor, minus, for an incoming gluon, k times the position of the field, which is n bar times t. And now we need to do the t integral. And the t integral, you see, I hope I get the sign right. The t integral brings down minus I n bar dot k. And then we get minus I t n bar dot k from minus infinity to 0. And at 0, this takes the value 1. At minus infinity, it's undefined. This is why I had put in the I delta in the when I introduced the Wilson line. So when you have the I delta, it adds here with the right, well, I don't know, with the right sign. So that, no, with the right sign. So it's e to the t times delta at t equal minus infinity, and then this vanishes for positive delta. And then you see what we get is exactly what we should get. N bar dot epsilon over n bar dot k. And I lost my color matrix somewhere. Yes, because of course here there's also a color matrix. Also a color matrix which sits here. And then you see that this is exactly this. Okay? So, in summary, we have this very important matching relation. Half of all SCET application papers start from this relation. This is anything that has to do with quarks in SCET, it's this relation. And there's a corresponding relation for gluons, and then it's Higgs physics. Okay? So, this relation is interesting because of the appearance of the Wilson lines. The Wilson lines, on the one hand, ensure gauge invariance. The Wilson lines, on the other hand, account for some real physics, namely that when I match this current onto SCET, there are some non-trivial hard matching contributions already at tree level, and there are infinitely many of them, because as soon as I have collinear fields and anticollinear fields in the same basket, in the same operator, I can attach collinear gluons to the anticollinear fields and get hard propagators in tree-level graphs. So there is a non-trivial matching. All these infinitely many tree-level graphs of the type I showed you, they collapse into structures where here I can pull collinear or anticollinear Wilson lines, all from the effective vertex in SCET, all described by these Wilson lines. And we check this at the poor man's level, at the one gluon level. Again, these are easy calculations, tree level. If you want, you can try to draw the diagrams at least, how this would look for two gluons. And it works to all orders. It works to all orders because, in a way, this is the unique thing we could write down that is gauge invariant. Okay. So this matching relation is very important. What we'll discuss tomorrow is basically, so we saw there is a non-trivial tree-level matching, which gives the Wilson lines. There's also a non-trivial one-loop matching, which gives a Wilson coefficient in front here. We'll study the Wilson coefficient in front. In our Sudhir form factor problem, that was the hard contribution, which we found at one loop, which was non-trivial. So that we'll have to discuss. Then we'll discuss how this Wilson coefficient runs with the scale mu, which renormalization group equation it satisfies, how one solves this equation, and how one proves factorization based on these constructions. And then after tomorrow's lectures, which are my last lectures, I will upload another lecture, which I will not give to you because it has many plots of experimental data and long equations. It's an application. It's an application to a really physical problem. The physical problem is the thrust distribution in E plus E minus to two jets, what we are discussing here, but really then computing the cross-section for thrust and comparing it to the data. And this is something, you know, when you, sit in the train and go home, you can look through it. It's just full of plots and also equations that are too long to put them on the blackboard, but I thought it might be useful to see a real application. It's a paper written by some colleagues of mine many years ago where they did a SCET-based prediction, including resummation for the thrust distribution, which is one of the ways of extracting alpha strong. It's actually something physically also very interesting. So just as an upshot, we'll continue with this relation tomorrow and discuss the loop corrections, the hard loop corrections to it, and the RG evolution and so on and so forth. And then the application will be given as a bonus material for you to read when you have the time. What happens if it's not a, do you have an example of not a color neutral current? You mean a color octet current? Oh, sure. No, I mean, you will not have a two-jet process with a color octet current. That does not appear in physics. What do you mean? So what's the process that you... Ah, you mean dijet, okay. There you have beam remnants which carry the color, yeah. Let me think about it if I can say something useful tomorrow. We break, right? And then we have to discuss, we break now.